Welcome to this webinar. And in this webinar, we'll go through the process of setting the EM simulation setup and post-processing the results. So as a recap, in the last webinar, we finished by we finished the project by saving the mesh file. So in the now we can see the view that from Nullspace prep that we have done the meshing, and if I open the journal file now, then you can see that we have saved the mesh file in the cube file format, and we have assigned the name 16 gigahertz patch antenna. So we will use this mesh file and import it into the Nullspace EM simulation setup. And for the EM simulation setup, everything is done in the Python environment. And with that, then we need to create two Python files, one for the simulation setup and one for the post-processing. So right now, what you're looking is for the simulation setting. So we create a Python file called sim.py, and you can assign different names as well, and then import the Nullspace EM library and SEM. And right now also we import another Python library called NumPy just for mathematical operations. So for the simulation setup, we need to configure a simulation name. Right now, I'm using this config parameter and assign a string for that, and that's the name that we use for the the Q5 file that we saved in the last webinar. So I'm using that as a config name. And for the simulation, I will use that in the configuration. So I'm using the configuration object and use the config, the 16 gigahertz patch antenna plus a postfix. So I'm assigning a name for the simulation and call that object as a model. So that would be the simulation model. So, and then for that simulation model, then we need to assign the mesh file. So we can go ahead and then write model that set underscore q5 underscore file name and put the corresponding mesh file. So in this case, then would be the 16 gigahertz patch antenna.cube5. So now we load the mesh, and we start to assign different simulation settings. So we can start by setting the basis order function. So you can do so by writing model.set underscore order. And in Nullspace EM, we have three different orders. With number one is with being the lowest order, and then 3 is the highest order. And by default, it's always set to 1. So in this case, we are using 1. And after that, we want to adjust the scaling. So the thing that you have to always remember is that in Nullspace EM, the unit for dimension is meter. And if you're using something else than meter in Nullspace prep, then you need to do the conversion. So this is quite a necessary step to do to avoid any errors. So in this case, for this project, we use mil, and then now we do the conversion to meter by setting the set underscore model dot scale. And next step is to set the frequency range. You can do so by writing model.set underscore frequencies. And right now I'm using a NumPy array, creating a NumPy array and setting the frequency from 15 to 17 gigahertz with 51 samples. And note that in Nullspace EM, the unit for frequency is in gigahertz. So to consider that. And after we set the frequency range, then we save the model by writing model.save. So that was the simulation part. And now we want to make a configuration for the report that the probes that we want to look at, or the parameters that we want to look at when we do the post-processing. So we can do this similar way. So we can create an object called report, and we need to assign a name for the report. So I'm using the same config, the patch 16 patch antenna, and I'm also adding a postfix to that. And we need to also refer to the simulation name, so simulation file that we use. So we on the second part, that's the simulation name that we assign, and assign a name for that called report. And now we can start to request the parameters we want. So first we want to look at the y parameter. So we request the y parameter by writing report.request underscore y underscore parameters. And from these, then we can extract the S parameters, input arms. And we also want to look at the far field pattern. To be able to do that, we need to first define the scanning range in the spherical system. So we need to define the scanning range on the theta and phi domain. So you can do so by creating an NumPy array. This will generate the theta values from 0 to 180 degrees with a step of 2 degrees. And similar way, so for the phi, then we create a NumPy array from 0 to 360 degrees with a step of 2 degrees. So once we have done that, then we can go ahead and then request the far field. So we can do that by writing report.request far fields and then agreed. So the input, if you move on the top, then you can see what you need to give as an input. So I need to theta and phi. We avoid the last parameter. So we can just put the theta and phi as an input. So that was for the far field. And if you want to look at the near field data, then you can do so first by assigning the cut plane that you're interested of. And in this case, if you go back to Nullspace prep, then we want to look at the cuts along the feed point. So it will be ZX cut. So we can do so by adding a plane called, you give it a name first, and then I'm assigning the range for the Z and the number of samples, and I'm assigning the range for the X, the number of samples, and the position, the location of the cut. And then now I'm assigning the cuts that I'm interested. After that, then we can request the near field. So we can do that by writing reports.request underscore near underscore fields. And you can set the parameters for this as well. So we can set the field type. Now, in this case, we're setting the scatters, and we are requesting the absolute value.
Progress.
And you are able to also request the real and imaginary part as well. Another feature that Nullspace EM provides is to request a paraview. So we can use the paraview software to visualize the fields, far field, near field, and surface currents, which I will later show on. So now we are requesting a paraview by setting the properties. So now we are assigning the type and number of samples here. And the last thing that we want to look is the surface current. So we want to look at the surface current, and we can request that by similar way, writing that report.request underscore surface underscore currents and the properties of the type, and we are requesting the absolute value in this case. So after we set all the configuration, then we can go ahead and save the report by writing report.save and and then running the simulation. And once the simulation is done, then we run the report. So once we run this, I have already run this. So you will get 4 different files. So two for the simulation and 2 for the report. So you can see here that I have 2 files in one in H5 format that includes the data, and then the .out format that includes the log data. So for example, if you look at the log data, then you can see the info of the log data for the simulation process, and then the H5 includes actual data, and then the reports includes the what we have specified to look at. So now we can go ahead and look at the post-processing part. It is a similar way. So you create a Python file. In this case, I have named it postprocess.py. And we need to import the libraries that we need. So in this case, we want to be able to plot the data. So I'm using matplotlib library and NumPy for calculation and Nullspace EM post-processing library. So it's a similar way. So we need to load the report file. We can do so by calling the object called postprocess and setting loading the corresponding file, report file. In this case, then I have set that to 16 gigabytes patch antenna plus the postfix that I have defined in the simulation. And we call that a post. We call the variable name post for that, and we start to extract the data that we want. So we want to extract the frequency. You can do that by writing post.get under frequencies. That will give you the frequency vector, and you can assign a name for that. After that, we want to look at the S parameters. So you can do that by writing post.underscore S parameters. And you can see that the S parameter is a matrix and the dimension includes the first dimension is number of sources we have, and then the last dimension is number of frequency we have. And in this case, now we have named it as S. And we want to be able to extract the return loss. So we can do so by extracting the return loss from the S parameter. So in this case, we only have one source. So I'm just using the 0 index. And I'm extracting all the frequencies. And we are using a built-in function from Nullspace EM library to convert it to dB. So now we calculate the return loss, and another parameter that we usually look is input impedance. So we can do that by writing post dot get input impedance. So the get input the impedance is a matrix in the format of number of sources and number of frequencies. And to be able to extract the real and imaginary part, then you can use the NumPy functions, the real and imaginary, to extract the real and imaginary parts. And the last part that we wanted to look is the far field data. So first we need to extract the theta and phi vectors. We can do that by writing post.get underscore OBS underscore theta, and the similar for the phi. So we are extracting theta and phi, and the last is to get the gain. So we can write post dot get underscore gain. And here you can assign the polarization. So you're using a spherical in this case. And get gain is basically a 5D array. So it includes the number of points in the phi direction, number of points in theta, number of voltage sources we have, number of frequency, and the polarization, the core and cross polarization. And then we want to be able to extract the far field at a specific frequency or at a specific angle. Then you can also do that by getting the indexes for those. So for example, if we want to get the gain at the theta 90 degrees, then you can write first find the index for theta 90 degrees. So you can write that by post get underscore nearest, and that will give you the index for theta 90 the similar way. So if we want to extract the information at 16 gigahertz, we can write that get the nearest frequency to 16 gigahertz, and then that will give you the index for that. And we want to have a plot for phi zero cut as well. So we're defining that. We are extracting the index for that. And here we are extracting the board side gain and the gain for theta 90 and phi zero cut. So here we're defining a variable called g underscore board side, and I'm basically using the index for theta 90 degrees, and we have the voltage source that is the first. We have only one voltage source and all the frequencies and copolarization. And for the theta 90 degrees cut, then we have two, one for the copolarization and one for the cross polarization. So a similar way in this case, I'm also cutting it at the specific frequency that is at 16 gigahertz. So that will give you for copolarization, and this will give you for cross polarization. And we are doing the same thing for the phi zero cuts for the polarization and cross polarization. So right now we have extracted all the data that we needed, and then the rest is just making the plot. So now here I'm defining the plots that we need. So these are the plots that I'm creating the plots, a subplot. And now we can go ahead and start plotting the different results. So in this case, I'm plotting the return loss and setting the properties for the figure. So it is similar for different results. So this is for the input impedance. I'm plotting the impedance versus the frequency, and here we are getting the bore side gain or the frequency, and these two plots are for the pattern cuts. And the last we have the 3D pattern that we use the building function from the Nullspace EM library. So if I run this, then I will be able to see the results. So if you open your Nullspace EM environment and choose the right directory, and then you can write Python. Now I'm calling the post process Python. So once process the data, then we'll be able to get the results. So now I will so now we have the all the figures that we need. So just to, so you can see that we have the return loss, the S parameters over the frequency, and we have the input impedance. We have the bore side gain that we have defined over the frequency range. And then we have the pattern class that we have defined for theta 90 degrees for phi 0 with the copolarization and cross polarization. And we have a figure also that shows the 3D pattern at 16 gigahertz. So this is how you can post-process and analyze the data into the Python. And you can also do that by using the paraview. So if you want to use a paraview, then you can basically choose the directory. So if you open the paraview and then choose open and then choose the directory that you have your reports on, then you can open the data. So this will give you the near field, and this is for the far field, and these are for the objects or the structure and also for the surface current. I have already loaded this into the software, so I will skip the loading part. But here then you can see that if I select, this will give you the surface currents that we define. So now you get the top view here. So if you click in this icon 2D, then you would be able to get the 3D view and rotate the object. So now we have the surface currents, and then you can also add the near field that we have defined. So we have the near field defined here. Then if you press show, then you will be able to get the near field data as well. So you can analyze that. Then you can see also the intensity. So now you can see the fringing fields close to the edge of the patch, and you can see the currents on the edge of the patch here as well. So the last thing that we can add is the radiation pattern that we have already looked to the Python post-processing. So now we can add that on top of this. So you can also modify the transparency. So now we can make that, you can do a visualization or change the properties in ParaView and make animation also in this way. So this is a good way to have all the data, so all the fields in one place to be able to analyze the results and make also plots for the reports. And another nice thing that I like to do is the orthogonal slice cuts. So if I use that and then have the radiation pattern, then you can see I have the cuts, and if I move then I get the different slices across the pattern. So that's a nice way to be able to check the different cuts as well. So with this, I'm concluding this webinar that we talk about the EM simulation setup and post-processing results. So thank you for joining this webinar, and please let me know if you have any questions.